calculus students. So we're going to carry on learning about how to estimate the area with finite sums with two examples. Example 3, we are given an integral that we are being asked to estimate. So we can see here it says find the integral from 0 to 9 of the square root of x dx using 3 subintervals. So what this means is that I want to graph the square root of x, so you can see that I did, and I want to find the area underneath the square root of x from 0 to 9, but we're going to use an estimation technique. It says it wants 3 subintervals of equal length, so in order to find my change in x, remember, if it's equal length, your change in x will all be the same. I can take my endpoints, so my b minus a divided by n, that would be 9 minus 0 divided by 3, which is 3. So that means I have 3 subintervals, all of length 3, which is why in my graph you can see I labeled the bottom 0, 3, 6, and 9. Those are basically the endpoints for my subintervals. So if I start off with left Riemann sums, let's get a new color up in here. Let's do blue. Left Riemann sums means that at the endpoints of my subintervals, I'm going to use the endpoint on the left. So from 0 to 3, I'm going to choose to use 0. And so my first subinterval, since it starts at 0, there's really no rectangle here. It's a rectangle with a height of 0. So that's it for that. And now for my subinterval from 3 to 6, I'm going to use my left point at 3, and I'll go up to my graph. So that's right there. And so going all the way over to 6 will look like this. Here's that rectangle. Beautiful. And then from 6 to 9, I'm going to use the value on the left, which is 6. So I'll go right there, like this. And so my approximation of the area under the curve ends up just being those 2 rectangles. So the way that I'm going to write this, using my proper notation, will be the integral from 0 to 9 of the square root of x dx can be approximated as the base of all my rectangles is 3, so I can kind of use 3 in parentheses and then multiply times my heights. So the first height is just 0. The height of my second rectangle is the y value at the point 3. So the y value there is the square root of 3, because I'm just, remember, plugging it into this equation right there, the square root of x. I guess I can write this, f of x equals the square root of x. So this point is just the square root of 3. And then the last height is the square root of 6. Okay, if I were to multiply this all out, I would get 12.5446. And this would be, I'm asked to determine if the approximation is an over or an underestimate. So I was asked this question. And this is an underestimate. And the reason why, I'll use green, is because of all this space that is under the curve that my rectangles don't take up. So all of this green space is space that the rectangles are kind of ignoring. So the rectangles are an underestimate because there's all that green area that was never taken up. Okay. Now let's do this with right Riemann sums. So same equation, I use my same graph. You can see I just copied those before the video to save time. You can draw yours in right now though. And so now, from 0 to 3, if I'm doing right Riemann sums, I want to use the right point. So from 0 to 3, I'm using that value there, and here's my rectangle. And then from 3 to 6, I'm using the point on the right, which will look like this. And then from 6 to 9, I'm using 9 as my endpoint for that rectangle. So now you can see I have 3 very different rectangles because I used the point on the right instead of the point on the left. Okay. So using proper notation again, I'll say the integral from 0 to 9 of the square root of x dx is approximately, I'm using these curly Q equal signs, that represents an approximation because this is not equal. You don't want to ever say that this is equal to this because it's not, it's an approximation. And so all of my bases are 3 again. The height of that first rectangle is the square root of 3. The height of the second rectangle is the square root of 6. And the height of the last rectangle is the square root of 9. When we add all these up, we end up getting 21.5446. You can see it looks similar to this number because instead of a 0, we had this square root of 9 right here, which ends up being 3. And then 3 times 3 is 9. So this estimate is actually exactly 9 greater than the underestimate before. This is an overestimate. And the reason why, I'll use red, is because you can see our rectangles now are going over the area. So all of this red space is where the rectangles went over the actual area. So it's the area plus all that red space. So the first one's an underestimate, and then we have an overestimate. Now we need to use midpoint sums. So midpoint, remember, isn't using either the left or the right, it's using the space in between, right in the middle. So I need to determine the numbers in between 0, 3, 6, and 9. So I'm going to add points. The number right between 0 and 3 is 1.5. And then, as you can probably tell, we're just going to be adding 1.5 to 3. So 3 plus 1.5 is 4.5. Plus another 1.5 is 6. And then 6 plus 1.5 is 7.5. And then 1.5 plus 7.5 is 9. So that works out. So I'm still having length of 3, so the base of the rectangles will all be 3, but now I'm using these midpoints to kind of help me find where my point is going to be. So at 1.5, here is my height. I'm going to bring this all the way over to 3. And then at 4.5, here is my height. Bring it back to 3 and over to 6. And then at 7.5, here's my height. And I go back to 6 and over to 9. So this one, because I use the space in between, has some underestimation and some overestimation. So in green, I'll highlight where, oops, that was literally a highlight. I'll highlight where I underestimated, which is right here. That place wasn't taken up. Here's an underestimation. And then right there is an underestimation. And then in red, I will color where I overestimated. So my space is right here. Yeah. So this one, it usually kind of evens out. It's never exactly correct, but you can get pretty close with the midpoint. So the midpoint from 0 to 9 of the square root of x dx is approximately 3 times the square root of 1.5, since that's what this output is here. I plugged 1.5 into my function, which is the square root of x. And then my output at 4.5 is the square root of 4.5. And the output at 7.5 is the square root of 7.5. And this all ends up being 18.254. And this one, we kind of have to guess whether it's an under or overestimate. Maybe you could give a little guess. I think, well, give a guess before I say what I think. Do you think it's over or under? Say it out loud. over or underestimate? My guess is that it's an underestimate. I think it's pretty close, but it looks like there's more red. So if I'm looking at the red pieces, they look a little bit bigger. And so it means that the area was guessed a little bit bigger than it was smaller. And just for your own, a little note, the actual value, so the integral from 0 to 9 of the square root of x dx is actually equal to, I don't have to use the approximation symbol, it's equal to 18. So you can see how our guesses went. The underestimate was 12.5, overestimate was 21.5, and then the midpoint, which was pretty close. Oh, okay, so I think now I feel silly. I think I said because of the red, it was an overestimate, but then I wrote underestimate. Well, I guess that happens to all of us. Over, it's over. So if you said over, you were correct. Because the actual value is just 18. Cool. So you will see some problems that ask you to do Riemann sums that are equations, like we just did in example 3. But you will also definitely get tables. So we'll have to really get comfortable with tables and kind of understanding these values without necessarily graphing everything. And same thing with the equations. We don't necessarily have to actually graph these. And as we practice, hopefully you get more comfortable solving these out without necessarily having to graph it each time. So right here, we have a table that's showing the velocity of a car as it travels for 10 seconds. Estimate the distance traveled by the car using left Riemann sums and right Riemann sums. Okay, so I've got to do both. I want to make a note right away that I can see that the change in x between each of these, so if I were to make a little change in x, and the way that I like to do that is, well, I guess this is kind of like change in t, but t and x are both our independent variable. But the way I like to do this is kind of make a little arrow and just write how much it changed by. And I'm sorry, I should have put a space here. This is annoying. But right here, the change between 0 and 3 is just 3. The change between 3 and 4 is 1. The change between 4 and 6 is 2. So I'm just finding the difference between them. The change between 6 and 7 is 1. The change between 7 and 9 is 2. And then lastly, the change between 9 and 10 is 1. So these are our values of the change in x, all of these. And we can see that the change in x isn't the same. It's changing. And so what this is going to mean is that each rectangle has a different base. You can see some of them have the same base, but we're going to have to actually write out the area formula for each of these. So remember that the area is equal to the change in x times whatever the height is. And in this case, our velocity, the y value is our height. So the height you can think of as the y value, right? So the velocity values are going to be represent our heights. Okay, so when I'm doing my lefts, I'll do left in, do the left in this reddish color, that one. The left means I'm using all the numbers on the left. So basically, see how this little arrow is pointing over to that? That's kind of indicating what is the y value that we're going to use. And so the left number that my arrow is pointing to is going to be the y value that we're going to use. So basically, I can estimate the distance is approximately the area of each of the rectangles that we would make out of this. So the area of the first rectangle the base is equal to 3, and the height is equal to 0. The second rectangle we would make has a base of 1 and a height of 10. The third rectangle we would make has a base of 2 and a height of 11. And so on and so forth. So you could try to guess what I'm going to put before I do it. But that's it. So I have 1, 2, 3, 4, 5, 6 rectangles made out of these 7 possible times. So there's going to be 7 time values, but since I'm only choosing the ones on the left, the last time gets ignored. Okay? And so what this ends up being is 89 miles. 89 miles. Cool. And now let's do part B, which is the right Riemann sums. Oops, I want to do a different color. Let's do, I don't know, purple? Purple. And so for part B, in purple, now I'm using the y values on the right. So basically I'm going to be using these ones that my arrow is pointing to. Like that. Okay. So I'm still using the same change in x's. Those aren't changing, but my output value I'm changing. So now my distance is going to be approximately 3 times 10 plus 1 times 11 plus 2 times 14 plus 1 times 14 plus 2 times 15 plus 1 times 18. I snuck it in. And this ends up being 131 miles. Whoa, those are quite different. So you can probably imagine in part A we got an underestimate. So this one's under. And this one's an overestimate. And the reason why I know that is because look at the velocity, our y values. Our y values are increasing. So the graph, if we were to graph this, it would look something like our square root function that we did up here. So our square root function is constantly increasing. So it starts off increasing quickly and then slows down. And so the shape of the graph is going to be similar. And so just like in part A, when I did a left Riemann sum, it was an underestimate. Same thing happened in part A of example 4 because we had a similarly shaped curve. And so in part B, when we were doing right Riemann sums, since both of these data, the graph and the table, were increasing functions, we got an overestimate. Okay. So these are 2 examples of very common Riemann sums that you will see both on my quiz as well as on the AP exam. If you could do these, that's awesome.